This is a summary of 2 years of R&D in 30 minutes. So I'm gonna do my best to hit that 30-minute mark. Can everybody hear me okay? Coming through. All right. All right. So this is a summary of our 2 years of R&D on the Energy Data Vault. Its design, as well as two case studies of its application that we've worked through recently. The first of which studies the impact of COVID-19 on building energy consumption patterns, and the second on the measurement of demand response analytics during California's August 2020 blackouts. So before we get to the fun stuff in the case studies, we'll give you some background material, what this project is, how we decided on differential privacy, and then we'll go into how we applied it. So the Energy Data Vault project is a DOE-funded 3-year R&D project among a number of different stakeholders, 2 government labs, NREL, LBNL, City of San Francisco, as well as Recurve Analytics, that's us, the industry partner. The idea was to develop some sort of privacy-preserving data analysis system. That is, a system that we could issue a wide number of statistical queries against sensitive data, get useful outputs, and not unduly compromise the privacy of individuals in those data sets. All the work is open source, available online, edp.recurve.com. That's the EDV is sort of the wider DOE research project. EDP is Recurve's particular implementation of it. Extensive documentation on all the stuff that you'll see in this talk here. All right, so why would you fund something like the EDV? The idea is that there's significant untapped social and environmental value to energy data. Non-exhaustive list of use cases here: climate planning, grid resilience, demand response. But it's a problem which hasn't been completely solved. And part of the reason for that, it's not for lack of effort, it's quite a hard problem. It's one that largely because it's changed over time. So 10 years ago, energy data was collected on a monthly basis through like normal energy meters. Whereas over the last decade, we've seen the widespread deployment of smart meters. So smart meters measure energy usage at much finer time resolutions, hourly, and sometimes even finer resolutions like 15-minutely or minutely. So the privacy problem underlying the usage of these data has changed quite dramatically under our feet since the original policy was written around it. So the core of the Energy Data Vault is differential privacy. The core anonymization mechanism is differential privacy. Mechanically, it's not so complicated what's happening. Rather than return exact aggregate statistics of the data, differential privacy adds a bit of noise to make it harder to determine the contribution of any particular individual to those statistics. The noise is chosen in a very precise way. It's chosen so as to realize a certain mathematical definition of privacy, which we have written down on this slide. The idea of showing this definition is not to like go into any detail on what exactly it means and do calculations with it, but the point is that it's defined rigorously, and you can actually manipulate it mathematically and prove certain properties of statistics which have the property of differential privacy. I've rephrased the mathematical definition here in a way that's maybe a bit more intuitive to give you a sense for what the property of differential privacy is. When you say a statistic is differentially private, what you're saying is that no matter how much an attacker knows about the contents of a database, that is, they may know the data for every other individual in the database except one, the likelihood of identifying that individual's data from a given differentially private statistic can only increase by a fixed amount epsilon because of the release of that statistic. You call that value epsilon the privacy parameter. We'll refer to it a couple times throughout this talk. You may have noticed that in setting up this definition, we haven't talked about privacy in binary terms, private, non-private. Indeed, the regime of differential privacy accepts that there's no such thing as truly anonymous data. That is a statistic that has no information whatsoever about individuals in it. That idea is sort of trivially provable, right? Like a statistic has to have information about individuals in it. Otherwise, it's random noise, right? The individuals have to move the statistic in some direction, which means that there's incrementally some small amount of information about individuals on, no matter which statistic you're talking about. Differential privacy provides us a way of measuring that risk over the course of numerous data releases and capturing it in a particular number, the privacy parameter epsilon. So we'll refer to it a couple times throughout this talk. Small epsilon values add more noise to outputs and result in a higher privacy guarantee. Higher values of epsilon result in a lower privacy guarantee, but more accurate outputs. So like golf, lower numbers are better. All right, so that's what it is. Why were we interested in differential privacy as an anonymization mechanism? 4 key properties that stood out to us that led us down this road. And we'll go into some detail on each of them. It has non-catastrophic accumulation of privacy risk. That privacy risk is comparable among across different data releases. The property of differential privacy is quite versatile. You can apply it to unforeseen statistical tasks. And then finally, it's emerging as the gold standard in industry with like a swelling wave of open source tooling and methods that we can hopefully ride into new territory. All right, so a little bit of detail on each of these properties. What do we mean by non-catastrophic? So non-catastrophic means that privacy risk of differentially private statistics degrades gradually. As you do subsequent data releases, you can predict quite well how much additional risk you incur. That is in contrast to the catastrophic failure mode, where subsequent data releases may dramatically undermine the privacy guarantee of previous data releases. The simplest example of that is how overlapping queries can dramatically undermine the privacy of aggregation-based privacy methods. So if your privacy method is you need at least 15 people in a given statistic, and if you have at least 15 people and you add up their values, there's enough people there that any individual's data sort of hides in the crowd of that statistic. That works to an extent unless you happen to issue a query which overlaps with that population by a single individual. That's diagrammed schematically here. You just subtract the 2 statistics and you've revealed completely an individual's data. So it's catastrophic in the sense that you went from 2 statistics, which maybe on their own you could call anonymous, safe, and by their interaction, you completely reveal an individual's data. That might seem like a contrived example, but there's a wide variety of literature that demonstrates quite a number of other less obvious and even more effective approaches that make use of this weakness of aggregation. I'll give you just 2 really quick examples. We don't have time to go into too much detail. One quick one is in energy data, overlapping queries have a way of sneaking in sometimes in non-obvious places. These are PG&E's 15 by 15 data releases. So these are available online right now. These are aggregate energy consumption data by zip code on a monthly basis. And it just so happens that quite a number of times in this data set, from month to month, the number of customers in the aggregation changes by just 1. So inadvertently, you've sort of issued an overlapping query from month to month. Now, that's probably not a major privacy. It's certainly not a major privacy issue because, right, these are large aggregates across a month, large number of customers. There's variability from month to month. But the idea is that if you were to do more statistics with energy data, you would be likely to do this sort of month to month or week to week type of aggregation, and overlapping queries have a way of appearing in this sort of workload. Another sort of eye-opening example is the effectiveness of database reconstruction attacks against US Census aggregate data. No time to go into the details of this, but it's a really interesting attack that was able to re-identify something like 71% of the population in the United States from census statistics, which you wouldn't think would have that much information about individuals or be that easy to re-identify. So the idea of saying all this, of this talking about this non-catastrophic privacy risk property, is not so much that aggregation is completely worthless. Everything we've done with it has exposed everyone involved to major privacy risk, because it hasn't. I mean, it works to an extent. The problem is that it's really hard to predict how much is too much. How many statistics released with aggregation as a privacy mechanism are too many. And once you reach that threshold, the privacy harm is quite dramatic. So it makes it tough. It makes it tough to say, all right, we want to do more with this stuff. How much more can we do? On the other hand, differential privacy provides a mathematically provable limit to how much privacy can degrade from subsequent data releases. It's sort of almost trivial. It is basically trivial to prove from the definition of differential privacy, and it's fairly easy to do mechanically as well. You just add up epsilon values from subsequent data releases. All right, second property that drew us to differential privacy. The next three are much faster than that one. That one's that one, even going quickly through it takes a while. All right, the next three. Differentially, the privacy risk incurred across different data releases via differential privacy are comparable, say apples to apples, with a single parameter. This is something we encountered quite a bit in our work with COVID-19 analytics. We'd have a number of figures that we wanted to prepare. In this case, a histogram of changing energy consumption, and here's a daily average load shape plot. It's sort of hard to tell just by looking at them which one represents a bigger privacy risk and by how much. And differential privacy gives us a measure for that. We can give a particular number to the difference in privacy risk between the two. Third property that drew us to differential privacy is it's versatile. It's a property of a statistic which can be arrived at a number of different ways. There are quite a number of mechanisms that can realize differential privacy for a given workload. Laplace mechanism, Gaussian, sparse vector technique, which means it's adaptable to unforeseen statistical procedures, statistical tasks. This might seem sort of like a kind of abstract idea, something interesting to researchers, but it comes to bear in a quite concrete way. And it came to bear in a quite concrete way for us in working with energy data. And we'll go through a little thought experiment to illustrate it. So consider a population of 900 buildings, 900 commercial buildings. 899 of them are, say, office buildings, and they have an energy consumption which clusters around a mean of, like, say, 3 kilowatt hours. In that population, there's also a cement factory, which uses a lot more energy. We'll say something like 400 kWh. What we want to do is compute an average weekly load shape. So how much energy this group of 900 buildings used on Sunday, on Monday, on Tuesday, on Wednesday, so on and so forth. The values of energy consumption in this thought experiment I chose to meet 15 by 15 criteria. So there's at least 15 buildings. That 400 kWh is about 15% of the total of that population. You have 899 times 3 plus 400. It's about 15%. We'll add one more wrinkle to this thought experiment, which is that the cement factory only runs 1 day a week. Okay, so can you tell which day of the week the cement factory ran? Right, it's not a trick question. It's day 3, Wednesday, right? It sticks way out. Not only can you tell which day of the week the cement factory ran, but it's pretty easy to tell that you could get a quite accurate measure of its actual energy consumption from this aggregate statistic. You would just subtract the mean from the other days of the week from this mean. This turns out not to just be a thought experiment. This is something that we saw in MCE's data while preparing our COVID-19 analytics. we ran into a number of populations where all but one or two members of the population clustered around a mean with one or two outliers around 15% of the total. The idea there is that if we had naively applied the 15 by 15 procedure, which is suitable for certain types of statistics, it wouldn't have worked very well, would not have realized this sort of meaningful definition of privacy for this other workload. It was context sensitive. That's the problem with privacy defined in a procedural way rather than as a property of a statistic. Differential privacy, on the other hand, was fairly straightforward to apply to this sort of thing. We chose a mechanism that was suited to time series data, in this case, the vector valued Laplace mechanism, added the appropriate amount of noise to smooth out the effect of possible outliers. All right, last property that was interesting to us, and that is that differential privacy is emerging as the gold standard in industry for privacy protection. Aforementioned 2020 US Census is adopting differential privacy. Almost every major tech company has incorporated it somehow. And more importantly than that, they've released a lot of open source software that allows you to use those methods. High quality open source software, number of courses and textbooks being written for practitioners. This is Professor Joe Neer's textbook, hot off the presses, as well as detailed write-ups of the actual application by a number of companies. Right, so this is really in contrast to, like, say, 5 years ago, where all of this stuff was almost purely academic and any open source implementation was not security grade. Whereas now that picture has really changed. Okay, so this stuff is, maybe I've convinced you this stuff is interesting. Has it solved any real problems yet? We've had the chance to pilot it twice over the last 6 months. And we'll go into some of the details of what problems this technology allows us to solve. Our first pilot was to unpack the impacts of COVID-19 shelter-in-place orders on building energy consumption. We did this in partnership with MCE, who provided the data. What were we hoping to do here? Well, COVID-19 and shelter-in-place, massive impact on energy usage patterns. I mean, it's a essentially existential problem for the energy efficiency sector. As a result, we didn't have good anonymization guidance for the types of statistics that we wanted to prepare to understand that impact. As you saw from the outlier example, there was reason to believe that leaning on the existing precedent in this sector would lead to undue privacy risk. And also, we wanted to share this stuff with as wide of an audience as possible, right? We needed a credible anonymization approach because the wider we could share it, the more quickly the sector could understand and adapt to the massive problems associated with this change in society. Fortunately, we had a year and a half of R&D on this cutting edge privacy approach on hand, and so we were able to apply it. We managed to prepare hourly load shape plots, residential and commercial sectors, as well as the distribution of changing energy patterns broken down by economic subsector. I wish I had time to go into the details of this in this talk. This is like really fascinating and surprising stuff. These figures were presented at the California Energy Efficiency Coordinating Committee, the CAKE, by MCE to like a wide variety of stakeholders in the efficiency sector, thanks to these robust anonymization that we were able to provide with differential privacy. This pilot, so one takeaway from this pilot, this was the first time we had to choose a concrete epsilon value. All right, until now we had been working on tools to study like what the trade-offs were, privacy and accuracy, and here we had to choose one. Now, this is a tough question. It's not purely a technical question. I wish it were. I wish we could choose something cryptographically low for epsilon, but unfortunately, those values are just not usable. rather than try to solve this negotiation between the mathematical and social and political and legal sides of the problem in one go, we chose a really conservative target based on existing work. So we took the same epsilon value as Google for their COVID-19 community mobility reports, which is an epsilon value, a daily epsilon value of 1.76 per person, which we actually strengthened to not just daily, but across the entire analysis period. The question was, could we do anything useful within this exceedingly strong target for the privacy parameter? And we found that we were able to meet that privacy parameter for some useful statistics. I showed you clips of some of them at the beginning of this case study breakdown. Here's a summary of all of the statistics we attempted to prepare, not all of which met that target. And I think this is sort of that idea of comparability among that the differential privacy offers, right? We had a measure that said, okay, well, if we're doing a weekly load shape plot of smaller population, yeah, that's maybe a little bit too risky at this stage. There's a little bit more to say about this, but I don't think I have time, so I'm just going to skip over it. Anyway, point is, you can't manage what you can't measure, right? And having a metric like this was quite influential in the design process of which statistics would we choose to release to a wider audience. All right, second pilot. Also, if you thought the COVID one was fascinating, this one is also pretty awesome. Like this one's hot off the presses. We finished writing the report for this one 10 days ago, something like that. I mean, this stuff is so timely, so needed by the efficiency sector. This is our second pilot was to quantify the impacts of demand response during a particular day of California's August 2020 blackouts. So we need a little bit of background to set up the privacy problem here for this case study. This case study considers a particular day of energy usage in California. August 14th, 2020, massive heat wave in California, rolling blackouts across the state. I imagine a number of you on this call were affected by this directly. This is CAISO's real-time energy prices during that event. Normally they're $35 a megawatt hour. Here they skyrocketed over 1,000. It's just absolutely massive, massive event. Red dots across the entire state. This is a big problem for the grid, which utilities are searching for a solution for. One of the ways of attacking it is with a class of techniques called demand response. That is, try to reduce demand during these extreme periods. One way to do that is what OhmConnect does. So this is our partner in this case study. OhmConnect runs they run a platform which uses gamification mechanics to get people to save energy during extreme periods like this. So they send text messages to people asking them to reduce energy consumption if they're able to, and then they also pay them if they do so. This technique has quite the possibility to make quite a big impact. OhmConnect recently raised like 100 million from Google for expanding this platform. So it's like, yeah, pretty massive technology. But the challenge is it's not actually that easy to quantify how much energy was saved from this sort of intervention. Ideally you have a time machine, right? And you, in one universe, OhmConnect sends their text messages, people turn off their air conditioners, you can measure how much energy they use there. Get in your time machine, go back, don't send the text message, measure how much energy that population used instead. Now you've got a counterfactual, you can subtract the two and get an exact measure of how much energy OhmConnect's intervention resulted in. Of course we can't do that. In real life, the technique that's emerging for doing this is called comparison groups, in which you try to identify a cohort to serve as a control group for the population that you've treated with demand response. So to say that in a more specific way, to quantify the impact of OhmConnect's demand response, you try to find residential energy customers that have similar energy consumption patterns to OhmConnect's customers that were sent text messages, and then you subtract their average energy use from OhmConnect's customers. That the OhmConnect's customers we refer to as the treatment group, so they receive the demand response intervention. The control group, you call the comparison group. So this class of approach is called the comparison groups approach. All right, so that's the setup for the privacy problem. There's a privacy problem embedded in all of this, and that is that while OhmConnect has a relationship with their customers and can ask for consent to use their data for these sorts of analytics, they don't have a relationship with that comparison group. And indeed, the comparison group needs to be drawn from quite a large population in order to be representative enough to be used as a comparison group. So it's not realistic to ask for consent on such a large scale. So instead, we need some credible anonymization mechanism for those comparison group statistics. That's what differential privacy allows us to do. We start from a pool of buildings from which to construct a comparison group. That's done with stratified sampling. We end up with some subset of that population, which is the comparison group. Any statistic you run against the comparison group, you add noise to, so as to realize differential privacy for anybody involved in the comparison group. Here's what comes out. These are the actual differentially private statistics that we prepared with OhmConnect. Here's the treatment group energy consumption. These, because we have consent, don't have to apply differential privacy to. On the other hand, the comparison group has error bars around, around their data. That's the noise introduced by differential privacy. Then you subtract the two and you end up with total grid impact here, which the error bars carry over. This is another one that would be really cool to go into the building science for, but this is a privacy talk, so it would take a while. All right, we were able to do all of this within a very reasonable privacy budget, again, well below the target set during the COVID-19 work. Okay, so there's one big interesting takeaway from this that I wanted to point out. There's a tendency with, when thinking about this privacy problem, to look for a panacea, look for something that solves all your privacy problems in every case, all the time, for any data. But such a thing doesn't really, and differential privacy certainly isn't that, right? As you've seen, it applies only to aggregate statistics. It generally needs relatively large population sizes, so on the order of hundreds and ideally thousands. You can't release too many statistics about any of these populations. Otherwise, your privacy budget adds up too much. But that's okay. And I think that's what this second use case illustrates, I think, quite profoundly, that we didn't need anonymization for everything to unlock demand response analytics, and to unlock this sort of powerful approach to forecasting and dealing with grid demand. We just needed it in one key place. And that's where this tool of differential privacy fits in this compelling way. It's an exceptionally strong and versatile privacy guarantee that allows us this mechanism for high value statistics, which we aren't necessarily able to predict right up front that we'll need to, that we want to be able to compute. With that intervention, we can capture the social and environmental value of the data. All right, what's next? So last slide, the future of this work. In the coming year, we're hoping to pilot additional use cases. That's part of why we've organized the tag with such a diverse range of stakeholders. We're hoping to build out the policy framework for this approach to anonymization. This is ongoing work. We've submitted comments to 2 different data access proceedings nationwide so far. and are sort of evolving what language makes sense to integrate this into policy. And then finally, we want to, hand in hand with this sort of thing, continue to expand the methods for choosing epsilon values. We've worked with extremely conservative values until now, and I think we can continue to refine our understanding of the privacy issues to be smarter about choosing them. All right. Thank you guys. How'd I do? Did I get to 30 minutes?
Yep. So you're at 35. You might want to leave your deck up in case there's clarifications on specific